So now we're going to test the ADC, and you can see this time we now have an extra connection on our USB which routes through to a power supply, and that power supply is going to be asked to generate voltages on ADC channel 3, and we have the multimeter reading those voltages. Follow that cable back to the DMM, and we will also be getting the ADC to read those voltages, and just as before with the DAC, we are connecting up to the Mega through the USB UART connector on serial 3. Okay, so let's switch to the software. Here we have the script that we've loaded into the Mega to test the ADC. As before, we've got some Scuppy commands. We're running on serial 3. And the first thing we do again is just check that the ADC is connected and that we can initialize it. And as before, it is just looping around looking for commands coming in on serial 3. And in this case, the command structure will look something like this. So we ask which channel we're going to use. We're going to be using ADC3. The reading mode, in this case continuous, the resolution 16-bit, and the gain to be used, in this case, in this example here, ×1. The command is passed and will be sent through to the ADC. Let's have a look at that. Here we go. Here we go. Sorry, the reading the voltage here. Read the voltage, and we're looking for a return code in case there's generated an error. And we're actually looping around to gain a number of samples of that, which I've decided in the script to base on the resolution. So for 16 bits, it would run through 15 samples. Okay, and that would then report back to our test program. So our test program, not dissimilar to the DAC, is using a power supply to generate a voltage, the multimeter to read a voltage, and the instrument control board to actually also read it via the ADC. And we say which instrument we want to say, ADC3 in this case, and where we want to start generating volts and where we want to end those volts and how we increment it. So we're going to increment in millivolt steps, stopping at 100 millivolts. The graph itself, and here's from a previous example, will capture the voltage read by the ADC and the voltage read by the DMM. But we're actually capturing a lot more information in the structure here, where you can see the volts that the power supply should be outputting, what we're reading with the ADC and what we're reading with the DMM, and the actual difference between the two of them. This is quite a high code, but here we go. You can see that's possibly not the best one to use. We're getting 3.7 millivolts when we should be reading 3.7 millivolts. Anyway, the difference between them is a very small amount of microvolts. So let's run this. So as before, you'll set it up. It's selected the power supply for us, select the multimeter and the instrument control board. We want to output to ADC3 across those values. So again, the first thing to do is set up the test program and ask for the instrument's identities, and then it will start looping through, and you can see the volts that it's being asked to generate incrementing here, and the graph is being generated as we go along. Now it's reasonably slow in this because not only is the DMM making multiple readings to average, the ADC is also making multiple readings to average. and there's with the power supply in use, there's quite a large settling time on a change of voltage as well. So I'm not intending to run this through to 100 millivolts, and it would just take too long. But here you can see that the values are being pulled in, and what the DMM is reading and what the ADC is reading is very, very similar. As the voltage goes up in millivolt steps, the actual readings that can be seen here as captured are progressing very linearly as well. And I think that adequately shows that the ADC is working. There are other graphs and across the whole range of the ADC output available in the write-up on element 14, which is linked as well. So I'll stop that, and I'm sure you'll accept that ADC is outputting a good is reading, sorry, not outputting, is reading a voltage pretty accurately.